Today we're going to look at what I like to call the ln rule. This rule doesn't have a proper name or an exact name, and if you're in Edexcel, it's not in the formula book. OCR people, you get it given to you. Edexcel, not so lucky. Here's the formula then. I call it the ln rule because the answer's got an ln in. It relates to the natural logarithm. However, you might call it the derivative over the function rule, whatever works for you. The rule says that if we have an integral, there's a function in the denominator and the derivative, the exact derivative is in the numerator, then we can integrate it by just saying the answer is natural log of the function plus c. And we put those modular signs around it because f of x could be negative. This rule is just a special case of the reverse chain rule, but I think maybe it's a bit harder to see. So personally, I would add it to your list of these are things to look out for, because it's a very common one. And as I say, if you're doing Edexcel, you won't be given the formula. So it's something that you have to clock, recognize, and use. So some examples of this are going to be something like integrating the integral of 2x over x squared plus 1. We can see there that the derivative of x squared plus 1 is 2x. So using that formula, using this new rule, we can say that the answer must be ln x squared plus 1. In fact, we don't need the modulus this time because this is always positive, but I'm going to leave them on anyway, plus our c. For those interested, I will show you where this formula comes from. As I say, you could simply use it by doing the reverse chain rule, but I'll show you a derivation using a substitution because it might make it a bit more concrete. So we are trying to integrate this. What we can do is we can do the substitution of u equals f of x, so the denominator. When we do a substitution, we want to find du dx, which in this case, we don't know exactly what it's going to be because we don't know what f is, but we can call it f dash of x. And then from here we can rearrange. We rearrange for dx, times by dx, and divide by this. We're going to get 1 over f dash x du. We then put that into the original integral. We're going to have f dash x divided by u, because that's what we've called this, times by dx, 1 over f dash x du. And hopefully you now see that these two cancel out, which means that we are just integrating 1 over u, which we know to be ln of u. Again, with the modular signs because u could potentially be negative, and the plus c, of course. And then finishing off, like all substitutions, we put u back in. What was u? It was f of x that we said at the beginning there, with the plus c, like that. So it's one proof of how to get to the formula. You don't need to be able to reproduce that, but it does help your understanding if you can see where the formula comes from. Now you just have to recognize that formula in the wild. Okay, the first example should be pretty quick. We're looking out for the rule. I'm not going to write down the rule because you're not given the rule in the formula book. So what we are looking out for is a function in the denominator, such that when we differentiate it, we get the numerator. The denominator is e to the x plus 1. What's the derivative of that? It's e to the x. So it follows the form, so we can use the formula. The answer is going to be ln, the denominator, with a plus c at the end, just like that. Do you think we need the modulus around this one? I'll let you ponder that. For the next example, we look at the denominator. And we see that the derivative of the denominator, the derivative of cos, is minus sign, but in the numerator it's only got a sign. So if you've seen the reverse chain rule video, hopefully you'll understand the technique where we add in what we want. We want it to say minus sign. If it said minus sign, all our problems would be solved because then the derivative of the denominator is in the numerator. Happy days, we'll win. But we can't just add in a minus, because we've now changed the question. So we have to add another minus on the outside. Those two minuses cancel out. Nothing in the integral has changed, but now the numerator is exactly what we want it to be in order to use the rule. Therefore, the answer to this integral will be the minus from the outside, and then we use the rule on this, ln modulus the denominator, and then, of course, as always, plus c. This is quite a fun one because up until now, we've not been able to integrate tan. But is that not what sine over cos is? This is the integral of tan. And another example here, we again look at the derivative of the denominator. If you are familiar with the chain rule, then you'll know the derivative is going to be minus 2x sine x squared. That's very similar to what it says in the numerator, but it's not exactly right. In order to make the numerator perfectly matched up to the derivative, we'd have to put a 2 here. Minus 2x sine x squared is now exactly the derivative, so the rule can be applied. However, we can't just go round adding on 2's here, there and everywhere. We have to leave the integral the same, so this time we have to divide by 2. Well, half times 2 is 1. We've not changed anything, but inside, everything is looking great to apply the rule. And this means that the final integral answer will be half from the outside, and then the inside it will be using the ln rule. ln of cos of x squared, n bracket, n modulus, add c. Over to you then, here's your exercise. Could you integrate minus 6x squared plus 4x, all divided by x cubed minus x squared dx? And where this rule comes into its own, and it really shines, is when we have to write an algebraic fraction as partial fractions. So I'll be assuming that you know how to do partial fractions. If you don't, go and read the textbook on that chapter, or wait until you've learned that in school and then come back to me. Welcome back. Now you know how to do partial fractions. We're going to see how the ln rule works when we need to integrate them. So here's an example question. Now, if you were to expand the denominator and differentiate it, you would not get close enough to the numerator. So we couldn't apply the ln rule straight away. But instead, what you could use is partial fractions. If you use partial fractions, then we can rewrite the big fraction here as 2 over x plus 2 minus 1 over 2x plus 3. And as you're getting used to this rule, I would probably recommend writing that as 2 separate integrals. So there's absolutely nothing wrong with separating it into 2 integrals. As you're getting used to the ln rule for multiple things, if you separate it out, you'll recognize one rule, apply it, look at the other one, recognize the rule, apply it. And as you get more used to it, then you can just apply it straight away. Looking at the first one, what's the derivative of x plus 2? So what's the derivative of the denominator? It was 1. There's not a 1 in the numerator though, so oh no, we can't apply the rule. But oh wait, what if we put the 2 on the outside, like this? Then this time I've not changed the integral. All I've done is I've moved the 2 to the outside. The integral is still the same. If I put the 2 back in, nothing would have changed. But now what's the derivative of x plus 2? It's 1. So straight away, if I put down the 2, we can apply this ln rule. So ln x plus 2. That's for the first one. What's the second one? What's the derivative of the denominator? 2x plus 3. The derivative is 2. But there's not a 2 here. Imagine if there were a 2 here. That would be great. But we can't just add in a 2. So we have to put a half on the outside. You can always check by timesing the 1/2 by the 2. Do you get 1? Do you get the original numerator? Yes. And on the left, timesing 2 by 1, you get 2. Is that the original numerator? Yes. Always check that. Sometimes students struggle with knowing, do I divide by 2 or times by 2 or do something else with 2? You can always check by comparing it to the original. In this case, now we've put the half on the outside. 2x plus 3, its derivative is 2. So we're in exactly the right position to put ln of the denominator and then add c. There's some things you can do to try and put the two ln terms together, but I'm going to leave it like that. And now for exercise B. Could you integrate 5x plus 17 all divided by 2x squared minus 4x minus 6? If you try the ln rule straight away, you'll see that it won't work. So you'll have to put it into brackets, put it into partial fractions, and use the ln rule twice from there. Let me know what you get below. Well, there you have it. Now you can use the ln rule like a pro. If you need more examples, do be sure to let me know. I'll catch you in the next one.